Most developers assume integrating artificial intelligence into Visual Studio Code requires installing a third-party extension, like Continue or Llama Coder. That assumption introduces significant, unnecessary risk. This split-screen flowchart illustrates the cost of that assumption. On the left, the standard extension middleware path introduces outbound network requests to cloud telemetry and spikes your system memory. On the right, a native pipe routes data strictly to your local loopback address at 127.0.0.1, keeping memory usage flat and secure. Underneath its graphical interface, Visual Studio Code operates as a sophisticated shell built to execute arbitrary processes and handles standard input and output streams. By utilizing those core operating primitives, you can build a secure, zero-dependency local AI assistant without relying on external plugins. Eliminating the middleware layer guarantees that your proprietary code never leaves your machine, restoring absolute data sovereignty while optimizing system performance. The foundation of this architecture is Ollama. It exposes a RESTful API directly on your machine's local loopback address. Instead of a plugin, Ollama runs as a background service, creating a client-server model that is entirely contained within your physical hardware. Because the network traffic never travels beyond localhost, you eliminate the external dependencies that introduce supply chain vulnerabilities. You retain precise control over every byte of data flow. Your proprietary algorithms and codebase snippets cannot leak to third-party cloud analytics servers because the connection simply does not exist. Treating the text editor and the language model as composable Unix-style utilities returns architectural control directly to the developer. To make this local architecture work, we have to account for the primary hardware constraint of local inference: video RAM. VRAM acts as a strict physical boundary. When a language model exceeds the available capacity on the GPU, the operating system forces the excess layers to offload via the PCIe bus into slower system RAM. That data transfer creates a severe bottleneck. The resulting drop in tokens per second throughput renders the model too slow for interactive coding tasks. This formula calculates your exact VRAM footprint. Memory equals the parameter count times quantization bits divided by 8, multiplied by a 1.2 overhead factor. For a 7 billion parameter model at 4-bit quantization, this resolves to 4.2 gigabytes, leaving comfortable headroom on an 8 gigabyte GPU. Compressing the model weights to 4-bit precision shrinks its physical footprint by 75%. The resulting model maintains its rigorous reasoning capabilities while fitting easily on consumer hardware. Calculating these exact memory limits is the necessary prerequisite to engineering a real-time, responsive coding assistant. But the model weights are only part of the equation. We also have to account for the key value cache, the mechanism that stores attention vectors and gives the model its memory of your current file. The key value cache memory scales strictly linearly. As the context window expands to 32,000 tokens, it requires approximately 4.5 gigabytes of VRAM. Added to the base weights, this pushes the total memory usage to the absolute limit on an 8 gigabyte card. To avoid memory crashes, you must manually tune these context limits based on the specific task. Use a restrictive 2K window for fast autocomplete functions, and reserve the full 32K window strictly for comprehensive codebase reviews. Managing the KV cache precisely is the primary lever for keeping advanced models responsive on constrained consumer hardware. With the hardware constraints mapped, we can build the software integration layer. The bridge to the model is the Visual Studio Code task system. By writing custom JSON tasks, you can capture the exact visual state of your editor, including file paths and highlighted text, and format it directly for the command line. The task runner extracts your code, packing it into a JSON payload via curl, and fires an HTTP request to the local Ollama server. Variables like selected text and file dynamically inject your active IDE context into the prompt string before execution. Passing the file variable grants the model immediate structural awareness of the surrounding logic, dependencies, and import trees. Sending an isolated snippet of code yields inaccurate suggestions because the model lacks architectural awareness. Injecting the full file path grounds the model in the actual structure of your project. For larger jobs, you can use standard Unix piping techniques inside the integrated terminal to bypass command line string limits and process entire files in batches. The native task system translates the visual state of your workspace into raw computational input, entirely removing the need for a third-party translation layer. This setup works, but intermittent coding workflows often introduce severe time-to-first token latency. By default, a Llama unloads idle models from VRAM after 5 minutes, causing a massive latency spike on your next request as it reloads from disk. Injecting Keep Alive -1 into your API payload locks the model permanently in VRAM, ensuring a zero-latency response. To fully automate this, we leverage Visual Studio Code's native event-driven hooks, specifically the run-on folder open property. By configuring a silent empty task to trigger the moment you open a project folder, the model is loaded into memory and warmed up before you type a single line of code. You can extend this logic with background watch tasks, which monitor the file system and automatically trigger model-based analysis every time you hit save. Combining API memory overrides with native IDE lifecycle hooks transforms a passive local server into an always-warm, zero-latency background agent. Recent updates to Visual Studio Code have introduced a native language models management interface directly into the editor. As this wireframe shows, the core editor infrastructure can now natively scan port 11434, detect you're running a Llama daemon, and populate the model picker with your local hardware. This provides a tactical advantage. You can use the native UI to instantly hot swap between a small, highly quantized model for real-time autocomplete and a massive 70 billion parameter model for deep code-based refactoring. There is one critical technical requirement. A model must support native tool calling capabilities to be visible in the VS Code agent selection mode. Because the IDE prioritizes cloud defaults, you must navigate into the settings and manually unhide your local models to make them visible. This native visibility gives you the exact ergonomic convenience of a commercial extension, while preserving your absolute control over the back-end infrastructure. The goal of this architecture is to treat artificial intelligence as a standard, offline Unix text processing utility, rather than a black box cloud service. This approach guarantees absolute isolation for your sensitive intellectual property. An air-gapped coding assistant remains fully operational during network outages and is completely immune to subscription fee changes. For secure enterprise and government environments that explicitly prohibit external telemetry, this zero-dependency configuration is a strict operational requirement. By mastering these native primitives, developers guarantee their codebase remains entirely sovereign, while successfully integrating high-performance local inference into their daily workflow.